This is a reminder that you should feel free to take as much time as you need to write all of the notes down and think about them. Pause the video at your own pace. Welcome everybody to the last video of the chapter. We've made it to section 4.9, day number 2, rational functions. Yesterday we talked about vertical asymptotes, and today we're going to talk about horizontal and oblique asymptotes. First up, horizontal asymptotes. Here's what they look like. Here's the same function example that we were using yesterday, and we know there's a vertical asymptote here because the graph will approach this vertical line and get as close to it as you want. However, here is a horizontal asymptote. And notice that as x approaches infinity, you can get as close as you want to the x-axis. It'll never touch it, it'll never cross it, but you can get as close as you want to the x-axis simply by choosing values of x that are large enough. Similarly, you can get as close as you want to the x-axis from the negative side by choosing values of x that are negative enough or large enough in the negative direction. So you can say that there's a horizontal asymptote at y equals 0. That's the line y equals 0 right here, the x-axis. What that looks like numerically is this. As x gets incredibly large, you can choose larger and larger values of x. F of x will get incredibly close to 0. That's what it looks like in the positive side. On the negative side, you're choosing incredibly large negative numbers, and as you approach negative infinity, the value of the function will get very, very close to 0. You can get as close as you want to 0 by choosing a large enough number. So here's the big idea. Horizontal asymptotes are determined by the leading terms of the numerator and the denominator when the degrees are equal. So check this out. Here we're going to have, in this function, we're going to have a horizontal asymptote. And I know that, I can predict that by recognizing that we've got the leading terms here, the degrees are equal. This is an x squared term, this is an x squared term. So when that happens, I'm going to predict that the horizontal asymptote is going to be 3/2. That's just what it is. Now, as you can see from the graph, that's what it looks like. We've got, as x approaches positive infinity, the function approaches 3/2, and as x approaches negative infinity, the function also approaches 3/2. The function will continue always to get closer and closer to that line, but never cross it. How could we predict all that? How could we know that without the graph itself? Well, one way to do that, here's the short version. The degrees are equal, so therefore y equals 3/2. 3/2. Algebraically, the way you could, that's method 1. Method 2 is to prove that. If you wanted to convince somebody, you could multiply. One thing you could do is you could multiply the numerator and the denominator by 1 over x squared. Like, take this crazy term and distribute it to all three of these terms here. You would get x squared in the numerator, x squared in the denominator. Like, this x squared times this x squared is this. And you get this and this and this and this and this. It distributes to all the terms. You put them all over an x squared term. I chose that because as you can recognize that as numbers, as the value of x gets incredibly large, these terms simplify down to just 1 over x and 1 over x squared. And when that happens, when x goes to infinity, then these terms will just start to disappear. They'll become incredibly small, and these will become even more small. Like, all of these terms will eventually go to 0, or go to as close to 0 as you want by choosing a large enough x value. And so these terms don't really matter very much when you're choosing x values that are very large. It basically boils down to 3/2, which is the horizontal asymptote. And you can get as close to 3/2 as you want by choosing an x value that's as large as you want, making these terms as small as you want. Here's another horizontal asymptote. This time I'm just going to do the simple version that you can just eyeball it up and say, well, 4 is equal to 4, therefore the horizontal asymptote is y equals -7/11. Done. Here, there is a horizontal asymptote. You notice that the leading term is 2x, and this leading term is x cubed. So these are not going to be, they don't have the same degree. So what you can do is you can create a term that does have the same degree. You can just write in a 0x to the third. Now the degrees are the same, 3 equals 3, so you can say that this leading coefficient over this leading coefficient is the horizontal asymptote. 0 over 1 simplifies to 0. It's going to have a horizontal asymptote at 0. Is there a graph? No, I didn't put a graph. If you wanted to convince somebody of that, if you wanted to kind of prove it, then you could multiply all the terms in the numerator by 1 over x cubed and all the terms in the denominator by 1 over x cubed. All these terms are going to simplify down. They're all going to be put over x cubed, and they simplify down to this. You've got a 1 here, and you've got these fractions here. Well, as x approaches infinity, as x gets larger and larger and larger, all of these 4 terms are all just going to get as close as you want to 0. So therefore, the function will get very close to 0 over 1. Remember, the 1 is still here, which equals 0. The graph of this rational function has a vertical asymptote at when the denominator is equal to 0. The vertical asymptote here is when x squared is equal to 0, therefore x is equal to 0. Vertical asymptote is 0. But I want to know where the horizontal asymptote is going to be and why. You can do that right now. Tell me about that horizontal asymptote. What is it going to be and why is it that way? So those were horizontal asymptotes. Here are oblique asymptotes. Let me give you a visual picture of what an oblique asymptote looks like. It looks like this. The dotted line is now diagonal. So they occur when the degree of the numerator is equal to 1 plus the degree of the denominator. So the numerator is 1 higher. Let's take a look at example 7. First of all, here it is, and let's ask about asymptotes. It's definitely going to have a vertical asymptote where the denominator is equal to 0. That's where x equals 2. Then let's factor 2x squared minus 3x minus 1. And actually, let's not factor. What we're going to do is we're going to divide. We're going to take this entire numerator divided by the entire denominator using synthetic division here. You can also use polynomial division, but I like synthetic division because there's less handwriting. So you have 2, that's the 0, which is 2, and you have the coefficients out front, and when you divide, you get 2 and 1, so that's 2x plus 1. And then you have a remainder of 1. That remainder, you don't write it down as r of 1, write it as a fraction. Remember, we're dividing this whole thing by x minus 2, so here x minus 2 is in the denominator, and then 1 is the numerator. 2x plus 1 plus the remainder over what you divided by in the first place. So now, here you can see, it's a lot easier to see the oblique asymptote in this version of the function. This function is exactly equal to this function, the original. But it's written in a format that allows us to see the oblique asymptotes really well. As x approaches positive or negative infinity, this term is going to go to 0. It's going to get incredibly small. It'll get as small as you want by choosing a large enough value of x. So the function itself is going to approach 2x plus 1 as x goes to positive or negative infinity. That's the oblique asymptote. You take the function, you divide it by the 0, and then you get this remainder, and when you eliminate the remainder, then you get where the oblique asymptote is. In this case, it's y equals 2x plus 1. And we can see that here on the graph. This function was divided by x minus 2, and we got 2x plus 1 with a remainder. Ignoring the remainder, you get the oblique asymptote. The remainder is an incredibly big deal right here, where in this neighborhood of x equals 2, it creates the it creates the vertical asymptote, and then it also creates this interesting behavior going on. But when x gets really large, when x gets really negatively large, if that's the way you can say it, it'll get as close as you want to this dotted line, this oblique asymptote of y equals 2x plus 1. Check it out. Graph this. F of x equals x squared minus 9 over x plus 1. So let's do our normal first vertical asymptote analysis. We've got we have to ask ourselves, when is the denominator equal to 0? Well, it equals 0 when x plus 1 is equal to 0, x equals negative 1. That's the vertical asymptote. Let's find the oblique asymptotes, because I can predict there's going to be one. This is a 2 and this is a 1 that you can't see. So the numerator is a degree that's 1 higher than the denominator. So when we divide these using polynomial synthetic division, we have the 0. Sorry, we have x plus 1 here, and we're going to divide it by negative 1. 1 down, multiplied by the 0, add, multiplied by the 0, add. We get a remainder of negative 8. Fine. So you can rewrite this original function here, x squared minus 9 over x plus 1, as this new function, x minus 1 minus the remainder 8 over x plus 1. Remember, x plus 1 is what we divided the polynomial by in the first place. It was the denominator of the fraction. This function is exactly equal to the original, but it's a lot easier to see what the oblique asymptote is, because as x goes to plus or minus infinity, this term will get smaller and smaller, as close to 0 as you want. And so therefore the function will get as close to x plus 1 as you want. That's what the oblique asymptote is. Y equals x plus 1. And you can see that here in the graph. We've got a vertical asymptote, and then we've got an oblique asymptote at y equals x plus 1. Notice something that goes on really strange here. The function goes down, crosses the oblique asymptote at negative 9 comma negative 9, and goes out this way. But eventually, if you zoom in, if you go far enough, it'll turn back around and start approaching the oblique asymptote again from the negative side, from underneath. So here, next example. Wow, we've got a lot of examples. 2x plus 3 over 3x squared plus 7x minus 6. We've got a vertical asymptote wherever the denominator equals 0. Factor it, and you'll figure out that, and I'm using bottoms-up method here. If you factor it, you'll find that x equals negative 3, or x could equal 2/3. In either of those cases, you'll get a 0 in the denominator. So therefore, that's where the vertical asymptotes are. And we can see that in the graph here. X equals negative 3 here, and x equals 2/3 here, vertical asymptotes. I'm going to predict that there are not going to be any oblique asymptotes, because in the original function, the numerator is not 1, the degree of the numerator is not 1 higher than the degree of the denominator. This is 1, and this is 2. And if you had, say, 2 and 1 down here, if they were switched, then you might have an oblique asymptote. But we don't. I think we're going to have a horizontal asymptote, because we can see that as x approaches positive or negative infinity, the function itself is going to approach 0. Why? Because the leading term here, leading term in the denominator is 3, and if you wrote in as 0x cubed, then it would be 0 over 3. Those are the two leading coefficients. And so then you're going to have a horizontal asymptote at y equals 0. Because the instructions are to graph, you might need some other helpful, useful information. The y-intercept, when x equals 0, you can figure out just by plugging 0 into the function, and you get 3 over negative 6, which is negative 1/2. So you can plot that point also. More useful information, when f of x, if you have to figure out when f of x is equal to 0. That'll be the x-intercepts. We've got the y-intercept when you figure out when x is equal to 0, you plug it in, you get 3 over negative 6. That's why you get negative 1/2. But what about the x-intercepts? That's when the function itself is going to equal 0. Well, the function is going to equal 0 whenever the numerator is equal to 0. So here's the numerator. 2x plus 3 equals 0. And so then you subtract 3 from both sides, and then you divide both sides by 2. And you get negative 3/2 comma 0, which is right here. So this rational function is graphed. If you know the following information, if you know vertical asymptote, horizontal asymptote, x-intercept, y-intercept, then you know a lot about this graph. Furthermore, you can take some test points if you want to figure out which side of the x-axis this is going to be, here or here. We remember that the multiplicity of the 0 is odd. There's only one of these zeros, and so therefore it's going to cross the graph here. You can get all that information from just the equation, and then with that information you can produce a pretty reliable graph. If we want to graph this, then we can see that there's going to be a vertical asymptote wherever the denominator is equal to 0. So we factor the denominator, we get these answers, x equals 2 or x equals negative 3, and you can draw those in first. They will look like this. Draw this at negative 3, this vertical line at 2. And so we know that the function is going to be broken up into 3 different intervals. Next, you can figure out that there's a horizontal asymptote because this degree here is 2 and this degree here is 2. So therefore, you take the leading coefficient, which is, it's invisible, it's just 1 and 1, and you say that g of x is approaching 1 over 1, or just the value of 1. Because you have the degrees here equal to each other, you can figure out what the horizontal asymptote is. It's y equals 1. So you can draw that in also. And right now, these 3 different asymptotes, 2 vertical and 1 horizontal, are going to really well help you define where the function is, because you know that the graph is going to get closer and closer all the time. So those are the asymptotes. You can take some, if you really don't have a calculator or a graphing calculator or Desmos or whatever, you can take some test points and figure out where they are. So test points over here would reveal that it's positive. Test points over here would reveal that it's negative. You can also find the y-intercept by plugging in 0 in for x, and you get negative 1 over negative 6, which is positive 1/6. That's how you get this point, 0, 1/6. It's an easy point to find, or easier point to find. And then you can figure out where the whole function g of x is equal to 0 by figuring out where the numerator is equal to 0. Solving that, you get plus or minus 1. So if g of 1 is going to be 0 because you get 0 in the numerator, g of negative 1 is going to be 0 because you get 0 in the numerator also. Next, graph this example. Are there any vertical asymptotes? No, because the denominator is never going to equal 0. At least there are no real values of x. You might get complex numbers or imaginary numbers, but there's no vertical asymptotes that way. Oblique asymptote, I can predict that there's an oblique asymptote because there's a 3 in the top and a 2 in the bottom. 3 is 1 more than 2. So what is that oblique asymptote? Here, I'll show you what that looks like using polynomial division. When you divide the numerator here by the denominator, you get this thing. It's a 2x. You only have to do this once. How many times does x squared go into 2x cubed? 2x times. 2x times this is 2x cubed. 2x times 1 is still 2x. And then you remember to switch the signs to make it negative, and negative here. So that means these cancel out, and you're left with a remainder of minus 2x, or negative 2x. You put that over what you're dividing by, the divisor, and you have 2x over x squared plus 1. This expression is exactly equal to, this expression here is exactly equal to the original. except that it's easier to see the oblique asymptotes. We've got, as x approaches positive or negative infinity, we realize that this term is going to disappear. It's going to vanish, go to zero, close to zero as you want it to. So we've got f of x is approaching the oblique asymptote of 2x here, y equals 2x, as x approaches infinity. Oh, we note that also that when you plug in 0 into the function, you get 0 out. So that must be a y-intercept and an x-intercept. 0, 0 is the x-intercept and y-intercept. Here's the oblique asymptote, which you can graph. And then you can take test points to figure out on which side this is going to be. So, for example, if you plug 1 in, you get a value of 1, 1 here. And if you plug negative 1 in here, you get also something you can graph. And then you can see that they approach from either side. Last example, here we go. So we've got, this is the last example of the entire chapter. This is the numerator, and we notice that when you factor the denominator, you get x minus 2 in both. So first of all, when you factor the denominator, you get x minus 2 and x plus 1. Therefore, we've got vertical asymptotes at 2 and negative 1. 2 and negative 1. However, we notice that x minus 2 shows up in both the numerator and the denominator. So this function is exactly equivalent to the previous function, but it's not exactly equivalent to this function. You have to restrict the domain. You have to say that, well, yeah, they do simplify, but just make sure that x is never equal to 2, because if you did, then you would get a 0 in the original function. So maybe it's a lot easier to graph this one and just remember that x can't equal 2. There's going to be a hole. There's a hole in that graph, and the hole occurs where x equals 2. However, this rational function is a lot easier to graph because you can see we have a horizontal asymptote as x goes to positive infinity, and as x goes to negative infinity, both of these are going to go to 0. Because you have the degree of x equals 1 in the bottom. So we have a horizontal asymptote at y equals 0. We have a hole at where x equals 2. We have a vertical asymptote where x equals negative 1. And and then we have a y-intercept of 1, 1 here. From all that, you can kind of figure out where the graph is going to be. It's going to nuzzle up next to each of these asymptotes, have a hole here, have a y-intercept there, and no x-intercept. So, as Obama used to say, everyone start assignment 4I2, copy the problem list, and do the first problem. I'll see you in class.